Hello everyone, my name is Khan from UC Berkeley. Today I'll be presenting our work on language-guided world models. This is joint work with my collaborators at Princeton and USC. In this paper, we address the problem of AI's control, which is essentially how to get an AI's agent to do exactly what a human wants it to do. The key insight that motivates this work is that the internal structures of an agent constrain how efficiently a human can control it. Specifically, when a human faces a black box agent, they can only regulate the outward behaviors of the agent. In contrast, if the agents implement a modular, interpretable cognitive architectures, the humans can aim at influencing its cognitive processes, essentially teaching it what to think, in addition to teaching it what to do. We endorse a specific approach called model-based agent. In this approach, an agent builds a simulation of the environment, called a world model, and uses it to learn policies for performing tasks. Our key innovation is to enable the world model to be adapted via language-based communications. We call such a model a language-guided world model. A model-based agent can be controlled in two ways: by adapting its policies directly, via imitation or reinforcement learning, or by adapting its world model, which indirectly influences its policies. The second mechanism makes this type of agent efficient to control. Specifically, since all policies of the agents are trained within the same world model, changing the world model shifts the behaviors of all policies simultaneously. The ability to incorporate language feedback further enhances communication efficiency, as it allows humans to express complex intentions with minimal effort. Imagine that we can instruct a robot to handle all objects in a room carefully by simply saying, "The floor is slippery." We design a benchmark for language-guided world models based on the game of messengers. This game features a players interacting with multiple entities, each with a different set of attributes described by a set of language descriptions. The entities and their attributes vary from game to game, requiring a model that understands the language descriptions to accurately simulate a game. Our benchmark presents some of the most difficult problems in language crowding. First, it requires a model to interpret various linguistic concepts within a description. Some of these concepts are highly intricate, as they describe interaction among multiple entities. In contrast, previous world modeling benchmarks focus only on single entities concepts like color. To make the problem even more challenging, we demand a model to generalize to conversationally novel language description at test time. For example, we expect that a model that has seen a chasing dog and an immobile image to be able to simulate a chasing image. We designed three levels of conversational generalizations to provide a fine-grained evaluation of our model generalization capabilities. We frame world modeling as a sequence generation problem. Specifically, we convert environment trajectories into sequences of tokens and train models to auto-regressively generate these sequences. We propose a new architecture called AMR language-guided world models, which augment the transformers architectures with a specially designed attention mechanisms. We compare this approach with a no-language baseline, which ignores the language descriptions, and an encoder-decoder transformers, which is the state-of-the-art architectures in sequence generations, and finally an Oracle model based on ChatGPTs, which represent a model with a near-perfect parsing and grounding capabilities. Our results indicate the effectiveness of our approach. Our models outperform the transformers by substantial margin in all evaluation settings. While the transformers struggle with the harder setting, our model approaches the performance of the Oracle model on these settings. These results are significant because, to the best of our knowledge, our model is the first to demonstrate compositional generalized abilities on linguistic concepts that describe interaction among multiple entities. We illustrate an application of language-guided world models, in which these models enable agents to generate plans for humans to review and revise. Language-guided world models allow the plans to be modified by giving language feedback to the agents. This approach conceptually improves the safety and controllability of an agent, as it has to agree with the humans on the plan before taking action in the real world. In practice, we find that this approach leads to a 4 to 16 boost in reward compared to only adapting the agent via imitation learning. In summary, this work is our first step in demonstrating that agents with a modular, interpretable cognitive architectures can better incorporate human language feedback. These initial results are promising, and we are working to provide stronger theoretical and empirical evidence to prove the effectiveness of this approach. Thank you for listening.